Hey guys, what's up? Today we're looking at finding the partial derivative of a function using the chain rule, the multivariable chain rule. So what we want to do first is try to figure out how these compositions are really working here. So t is a function of u and v, but u and v are functions of p, q, and r. So ultimately t is a function of u and v, but it's really a function of p, q, and r because u and v are functions of p, q, and r themselves. So what we can do is we could say t is really a function of u, which is a function of p, and then q, and then r. And also it's a function of v, which is really just a function of p, q, and r. So let's try to think about this a little bit more clearly. So if we were to plug p, q, and r in for u, and p, q, and r in for v, then we would just get t as a function of p, q, and r. But let's keep it in mind that it's a composition. So what is u of 2, 1, 4? So let's try to evaluate u of 2, 1, 4, and then evaluate v of 2, 1, 4. And that's going to tell us what we can actually plug into t in terms of u and v. So u of 2, 1, 4, plug that in right here. That's going to be 2 times 1 times square root of 4. And that's just 2 times 2, which is 4. And same thing down here. Plug in 2, 1, 4 into v. So we get 2 times square root of 1, which is 1 times 4. So this is 8. So t of u equals 4, v equals 8 is the same as plugging in these values 2, 1, 4 into p, q, and r. So that's good to know, because in just a minute we're going to use this information to simplify our computation. So this is really, really important to note. All right, so this is our first application of the chain rule. If we want to differentiate t, this is what we're told to do, differentiate t with respect to p, well, we have to first go through the intermediate variables, in this case u and v. So differentiate t with respect to u, and then multiply that by the differentiation of u with respect to p, plus we have to take into account the other variable that depends on p, in this case v. So take the partial derivative of t with respect to v, and then differentiate v with respect to p. Now what we're going to do is plug in p equals 2, q equals 1, r equals 4 into each of these expressions. What is partial t, partial u? So partial t, partial u is equal to, differentiate this function t with respect to u. Let's see, that looks like a chain rule differentiation to me because I have a u in the bottom and then v is treated like a constant. So what that's going to give me is v, let's see, a negative out front because it's in the denominator. So it's like 2u plus constant to the negative 1. So differentiate, multiply by negative 1, then we get 2u plus v squared in the denominator, and then multiply that by 2. So really this is going to be negative 2v over this quantity 2u plus v quantity squared. Now, where do we evaluate this? We evaluate it when p equals 2, q equals 1, r equals 4. But we already said when p equals 2, q equals 1, r equals 4, that u equals 4 and v equals 8. So we can just plug in u equals 4 right here and v equals 8, and that's the same as plugging in p equals 2, q equals 1, r equals 4 to this if we were to actually plug in u equals pq square root of r right here and v equals p square root of q times r in for v. So we don't explicitly go all the way down to p, q, and r for this evaluation because we've already evaluated u and v at these p, q, and r values. So now evaluate this at 4, 8, and we get that this partial derivative, partial t, partial u at 4, 8 is equal to negative 2 times 8 over we get parentheses 2 times 4 plus 8 quantity squared. So this is negative 16 over 16 squared. So partial t, partial u, evaluated at u equals 4, v equals 8, which is equivalent to evaluating at p equals 2, q equals 1, r equals 4. This partial derivative is negative 1 over 16. So let's keep that in mind. And for the next term, partial t, partial v, we need to calculate a partial derivative of this function t with respect to v. And to do that, we're going to need the quotient rule. So we differentiate v with respect to v, multiply that by 2u plus v, minus the top, in this case v, times the derivative of 2u plus v with respect to v, over the denominator squared. So in this case 2u plus v squared. Now, this is going to be differentiate v with respect to v, we're going to get 1. So that just leaves 2u plus v right there. Minus, differentiate the parentheses here with respect to v, we just get 1. So 1 times v is just v. Over, and then we have that term 2u plus v squared. So really this is just 2u in the numerator. So this is just going to be 2u over 2u plus v quantity squared. And again, we want to evaluate this at the point 4, 8, because that is equivalent to evaluating p, q, and r at 2, 1, and 4. So evaluate this partial derivative at 4, 8. The numerator then is going to be 8 over 16 squared. So it's the same denominator that we had before. And then this is equal to, we reduce that to 1 over 32. All right, so we've got these two partial derivatives. We want to keep track of these throughout the whole computation because these two partial derivatives, negative 1 over 16 and 1 over 32, are going to be part of each computation that we do. So let's look at, let's go back and look at the original partial t, partial p computation. All right, so we're back at the partial derivative computation that we need to do. Partial t, partial p equals partial t, partial u evaluated at the point. Well, we know that's the same as just evaluating u and v at 4, 8. Plus, and we need now, or times partial u, partial p. So now we need to calculate partial u, partial p, and then evaluate that at 2, 1, 4. So partial u, partial p, just differentiate this function up here, u, with respect to p. We just get q times square root of r. Evaluate that at the points p equals 2, q equals 1, r equals 4. And that'll give us 1 times square root of 4, which is 2. So this number is going to be 2. All right, so that's our first piece on these partial derivatives that we need. And we also need partial v, partial p. That's the last part of our partial derivative. So partial v, partial p, differentiate this with respect to p. We get square root of q times r. And now I want to evaluate that at the point 2, 1, 4. That's going to be square root of 1, which is 1, times 4, which is 4. So these are our numbers that we need to stick into these 4 locations. So now these 4 locations are going to be negative 1 over 16. So that's the partial t, partial u evaluated at the point, which is equivalent to evaluating at 4, 8 for u and v, times partial u, partial p, which we know is 2 now. So multiply by 2, plus partial t, partial v, which is 1 over 32, times 4. That's equal to negative 2 over 16 plus 2 over 16, which equals 0. So this partial derivative is equal to 0. Partial t, partial p evaluated at this point is equal to 0. Right, so let's look at the next one, keeping this information as is because the next one is going to be very similar. So now we've got pretty much the same problem, except the independent variable we want to differentiate now with respect to is q. So all we have to do is look at this partial u partial q and partial v partial q. These other two terms, partial t partial u and partial t partial v, those stay the same. So those are exactly the same as what we had already. So partial u partial q is going to be p times square root of r. And now I want to evaluate that at the point p equals 2, q equals 1, r equals 4. So that's equal to, let's see, plug in 2 times square root of 2, which is 4. And then take the derivative partial v partial q. Differentiate v with respect to q. Let's see, q is under the radical, so this is going to be p times r over 2 square roots of q. And evaluate that now at the point p equals 2, q equals 1, r equals 4. So that's equal to 2 times 4 over 2 times square root of 1, which is 4. So we've got our partial derivatives, partial u partial q evaluated at the point. We've got partial v partial q evaluated at the point. All we have to do now is plug those in. So the same term, negative 1 over 16, but now it's times this number 4 plus 1 over 32 times 4. And that's equal to negative 1 over 4 plus 1 over 8, which is negative 1 over 8. So the partial derivative of t with respect to q evaluated at the point is negative 1 over 8. So now you've got the process. We've done it twice. Let's do it one more time. Let's see, partial u partial r is going to be equal to p times q over 2 square roots of r. So just differentiating that with respect to r. And now again, we want to evaluate at the point 2, 1, 4. And that's equal to, multiply, we get 2 over 2 square roots of 2, or 2 square roots of 4, which is 1 over 2, so 1/2. And then partial v partial r is equal to, differentiate with respect to r, we get p square roots of q. Evaluate that at the point, and we get that that's equal to 2 times square root of 1, which is 1. So this is 2. So we've got 1/2 and we've got 2. Now we plug those two values in up here. This is going to be equal to negative 1 over 16. That stayed the same the whole way through. Now this 1/2 is new, plus 1 over 32. That stayed the same all the way through, and times 2. So this is going to be negative 1 over 32 plus 1 over 16. This equals positive 1 over 32. And that's our final answer. And that's how we calculate these partial derivatives at points. It's much easier to plug in 4 and 8 into the partial derivative tu and tv than it is to like plug in what u and v are in terms of pq and r and then plug in pq and r values. That's my recommendation. That's how we do it.